Hi, this is Dr. Jim Wood, and welcome to another session of Psych 1303 Statistical Methods. Today is Class 21, Surveys and Polls, the Expected Value and Standard Error. Now, before we go into the lecture, let's review what we covered in the last lecture. In that lecture, we learned that a population consists of all members in a designated group. A sample is a subgroup of a population that's selected for the purpose of gaining information about the population. Political polls and surveys gather samples to learn about populations. So, for instance, a pollster may phone a sample of voters in a state and ask them how they plan to vote, so that the pollster can estimate how all the people in the state plan to vote. In this case, the population consists of all voters in the state, and the sample consists of the voters that the pollster calls. In the last lecture, we used the fictional example of Christina Green, who's running for governor of East Virginia. We talked about how pollsters conduct polls in order to learn how many people in East Virginia plan to vote for Christina Green. We said there are 8 million voters in the state of East Virginia. These 8 million voters make up the population of interest. The crucial question is, who will these 8 million voters vote for? 55% of the members of this population plan to vote for Christina Green. We say pi equals 55%, or pi equals 0.55. Pi is the symbol for this proportion in the population. A pollster then interviews 1,000 randomly selected voters in East Virginia and asks them how they plan to vote. These 1,000 voters are the pollster's sample. The pollster wants to use this sample to learn how voters in the population, that is, in the population of all East Virginia voters, how the voters plan to vote. The pollster learns that 54% of the voters in the sample plan to vote for Green. We say P equals 54%, or P equals 0.54. P is the symbol for this proportion in the sample. So pi, the proportion in the population, is 55%. P, the proportion in the sample, is 54%. The two numbers are close, but not exactly the same. P is supposed to be an estimate of pi, but it isn't a perfect estimate. It's bound to be off a little. The difference between P and pi is called the sampling error. It's the amount that P is off as an estimate of pi. In this case, we subtract pi from P and find that the sampling error is negative 0.01. This is how much P is off as an estimate of pi. Now, during the last class, we also learned about the sampling distribution. I said that the sampling distribution is the central idea in this class for the next 3 weeks. And I advised you to really study this topic now by reviewing your lecture notes and doing the readings and homework. You really need to understand right away, right now, what a sampling distribution is, so you can make sense of what we're talking about during the next few lectures. If we want to understand what a sampling distribution is, probably the best approach is to understand how it's made. 5 steps are necessary to make a sampling distribution. First, we begin with a large population. In the Christina Green example we've been using, the population of East Virginia is 8 million people. That's the large population we start with. The second step is to collect a large number of separate samples from that population. For instance, in our example, we imagine we collect 700 samples of voters from the population of East Virginia voters. K is the number of samples we choose. So in our example, K equals 700. The third step is that each of these samples must include exactly the same number of individuals. For example, in the example we're talking about, we imagine that each of our samples includes exactly 1,000 voters. N is the number of individuals in each sample. So in this example, N equals 1,000. The fourth step is to calculate P for each sample. In our East Virginia example, P is the proportion of individuals in each sample who plan to vote for Christina Green. So in our first sample, we find that P equals 0.543. That is, 54.3% of the voters in sample 1 plan to vote for Green. And we write that number in this Excel sheet. In the second sample, we find that P equals 0.567. That is, 56.7% of the voters in sample 2 plan to vote for Green. And we write that number in the Excel sheet. We continue doing the same thing for all 700 samples. Our spreadsheet gets very long with 700 rows, and each row lists P for a different sample. So we have 700 values of P in this list. The fifth and final step is to take all 700 values of P and plot them as a histogram. This histogram shows the sampling distribution. This histogram shows the sampling distribution for P in our example. The bars show how many samples had which values of P. So for example, the bars in the middle of the graph are very tall. The height of the bars in the middle tells us that many samples had a value of P close to 55. The bars on the left and right end of the graph are very short. For instance, on the far right of the graph, there's a short little bar close to 0.61. Because this bar is short, we know that only 1 or 2 samples had a P of 0.61. At the end of the last lecture, we talked about how to estimate the standard deviation from this histogram or any histogram that is normal or kind of normal in shape. We begin by estimating 2 scores. First, we estimate the score that's equal to the mean. 0.55 is a good estimate of the mean in this histogram. Second, we estimate the score that is at the 97.5th percentile. 0.58 is a pretty good estimate for the 97.5th percentile in this histogram. When we're estimating these 2 scores, we just make our best guess. We want to estimate these 2 scores because we know they're 2 standard deviations apart. The z-score of the mean is 0, and the z-score equivalent to the 97.5th percentile is 2. We know that 0.55 and 0.58 are 2 standard deviations apart because their z-scores are 0 and 2. The distance between them is 0.03. So this distance must be equal to 2 standard deviations. If we divide 0.03 by 2, we get 0.015. This number, 0.015, is equal to 1 standard deviation. So 0.015 is our estimate of the standard deviation of the distribution. So that's it for last lecture. Now we're ready to go on to new topics. To begin with, let's clarify the difference between three kinds of distributions: the sample distribution, the population distribution, and the sampling distribution. Now, you've met all three of these distributions before, so what I say won't be entirely new. But it's important to have a clear distinction in your mind between these three types of distributions. To help explain the distinction between the three types of distributions, we'll be using the same example from the last lecture of Christina Green and her race to become governor of East Virginia. Let's begin with the sample distribution. A sample distribution is the distribution of a variable in a sample. So, in our East Virginia example, a pollster interviews 1,000 randomly selected voters. These 1,000 voters are our sample. The pollster finds that 54% of voters in this sample plan to vote for Green. This gives us enough information to construct a sample distribution. So here's the sample distribution. It's just a density histogram. The x-axis indicates how voters plan to vote regarding Christina Green, yes or no. The y-axis indicates the percentage of voters in each category. In this sample, 54% of the voters plan to vote for Green. The two categories on the x-axis are yes and no, but this is a dichotomous variable with two values, and a dichotomous variable can be turned into a Bernoulli variable like this. There we go. In this version of the graph, a 1 indicates a voter who plans to vote for Christina Green, and a 0 indicates a voter who does not plan to vote for her. We can now use what we know about Bernoulli variables. We know that P is equal to the number of individuals with a value of 1. So P equals 54% or 0.54. With the Bernoulli variable, P is also equal to the mean. So if we add up all the zeros and ones for the 1,000 voters and then divide by 1,000 to get their mean, it will turn out to be 0.54. Now let's talk about the population distribution. Ask yourself, what is the population of interest in the example we're using? Okay, the population of interest in this example consists of all 8 million voters in East Virginia. In this population, 55% of voters plan to vote for Green. So pi is equal to 55%. Now this gives us enough information to construct a population distribution. Here's the population distribution. The x-axis again indicates how voters plan to vote regarding Christina Green, yes or no. The y-axis indicates the percentage of voters in each category. In the population, 55% of the voters plan to vote for Green. Now, you probably noticed this population distribution looks a lot like the sample distribution. For instance, the population distribution has 2 bars, and so does the sample distribution. If a sample comes from a certain population, then the sample distribution and the population distribution usually look fairly similar to each other. Now again, in this graph, the values on the x-axis are yes and no. And again, we can replace them with 1 and 0. So we have a Bernoulli variable. A 1 indicates a voter who plans to vote for Christina Green, and a 0 indicates a voter who does not plan to vote for her. We know that pi is equal to the number of individuals with a value of 1. So pi in this graph equals 55% or 0.55. So if we add up all the zeros and ones for the 8 million voters in the population and then divide this sum by 8 million to get the mean, we know it will turn out to be 0.55. Now finally, we come to the sampling distribution. This is the sampling distribution of p for our example, and of course you've seen it before. The x-axis represents possible values of p, and the heights of the bars indicate the number of samples with each value of p. Two features in particular set the sampling distribution of p apart from the population distribution in the sample distribution. So there are two features that make this distribution different from the other two. First, the shapes are different. The sample distribution and the population distribution for p each includes only 2 bars. In contrast, the sampling distribution is more or less normal in shape. Second, in the population distribution and the sample distribution, the variable is dichotomous. The variable can only take on 2 values. Yes will vote for green, or no will not vote for green. In contrast, in the sampling distribution, the variable p is continuous, not dichotomous. It can take on many, many values depending on the proportion of voters in a sample who plan to vote for green. So p can be 0.501, 0.540, 0.533, you name it. There are all sorts of values for p. So that is the difference between the sample distribution, the population distribution, and the sampling distribution. Now that we have that clearly on its mind, let's focus for a while on the sampling distribution, which, as you remember, is the central idea in this and following lectures. We're going to discuss the expected value of the sampling distribution. The mathematical symbol for the expected value of the sampling distribution of p is shown here. It's a capital E with little p in parentheses. And this symbol means the expected value of p. Now, don't let the long name worry you. The expected value of p in the sampling distribution is a very simple thing to understand, because the expected value of p is simply the average of all the values of p in the sampling distribution. Here's the Excel sheet that you saw before. This Excel sheet lists the value of p for all 700 samples in the sampling distribution. Now this slide shows only the first part of the sheet down to the 17th sample, but the sheet keeps going on and on and on until it lists 700 values of p, 1 p for each sample. Well, if we took these 700 values of p and calculated their mean, their average, that mean would be this expected value. It's that simple. It's just the average of all the numbers in that column. On this histogram of the sampling distribution, the expected value is right where you would expect it, since it's an average. It's right in the middle of the distribution. In this sampling distribution, the expected value of p is 0.55. Now, you may be wondering, why don't they just call it the mean instead of the expected value? Why do these statisticians make life so complicated? Well, here's why. Remember, we're now talking about three kinds of distributions: the sample distribution, the population distribution, and the sampling distribution. If we just say the mean was 55, then it's unclear whether we're referring to the mean of the sample distribution, the mean of the population distribution, or the mean of the sampling distribution of p. So, to avoid confusion, these three different means are given different names. The mean of a sample is called p, the mean of a population is called pi, and the mean of a sampling distribution of p is called the expected value of p. Now, here's a very useful fact that you'll use a lot during the next few weeks in this course. The expected value of p is equal to pi. Now, remember, the expected value of p is the mean of the sampling distribution, and pi is the mean of the population. So when we say the expected value of p equals pi, we're saying that the mean of the sampling distribution is the same as the mean of the population distribution. And this fact is not obvious. Let me show you why. First, let's talk about the population distribution. This is the population distribution, which we saw before. It represents the results for all 8 million voters in East Virginia. Each voter is assigned a value of 1 or 0, depending on whether the voter plans to vote for Christina Green or not. If we take these 8 million ones and zeros and average them, we get the mean pi. In this example, pi is 0.55. Now let's compare that with the sampling distribution. In the sampling distribution, we have 700 samples, not 8 million voters. And for each sample, we have a value of p. P is continuous. It can take on many values such as 0.541 and 0.573, you name it. Yet if we take these 700 values of p and average them, we find that their mean, the expected value of p, is the same as pi. In this example, the expected value of p and pi are both equal to 0.55. So the point is that the expected value of p and pi come from completely different distributions with different variables, but p and pi always turn out to be equal. The expected value of p is always equal to pi. Next, let's talk about the standard error of the sampling distribution. Its symbol is shown here. Capital letters SE with a small subscript P. This symbol is read as the standard error of P. Now, this is another case of a very long name for a very simple idea. The standard error of P is simply the standard deviation of all the values of P in the sampling distribution. Here's the same Excel sheet that we looked at earlier. It lists the value of P for 700 different samples. A few minutes ago, we took these 700 numbers and averaged them to get the expected value of P. Now we're going to do something similar. We're going to take these 700 numbers and calculate their standard deviation. The result we get is actually a standard deviation, but its official name is the standard error of P, because we want to keep the standard error of the sampling distribution separate from the standard deviations of the population and sample. Now, as I explained in the last lecture, we can draw 5 lines like this on a normal distribution. The distance from one line to the next is approximately equal to 1 standard deviation. But because this is a sampling distribution, we call the standard deviation the standard error. So the distance between each line and the next in this histogram is 1 standard error. These lines are about 0.015 apart. Yeah, they're about 0.015 apart. So the standard error is approximately 0.015. Now here's a useful fact about the standard error of P. The standard error of P is equal to sigma divided by the square root of n. Now, I wonder if you can possibly guess what sigma means here. I haven't told you yet, but maybe you have an inkling. Sigma is a Greek letter that is like our letter S. Statisticians use sigma as the symbol for the standard deviation of the population. So, if we took those 8 million ones and zeros in the population distribution and calculated their standard deviation, we would get sigma. N is the number of individuals in each of the samples in the sampling distribution. In our East Virginia example, we said that N equals 1,000. That is, there are 1,000 individuals in each sample. Okay, so we now have learned that the mean of the sampling distribution is called the expected value, and that the standard deviation of the sampling distribution is called the standard error. And we've learned some formulas that allow us to calculate the expected value and standard error. There is one more important fact about the sampling distribution that you should know. Its shape. As you can see, the sampling distribution is normal, or at least very close to normal. And in most cases that you'll run into, the sampling distribution will be normal or close to normal like this one. Statisticians say that the sampling distribution of P is normal if N is fairly large. Now, you notice that this is a bit vague. What size of N is fairly large? For practical purposes, you can assume that the sampling distribution of P is normal if N is 30 or more. As you remember, in the East Virginia example, N is 1,000. That is, there are 1,000 individuals in each sample. That's a lot more than fairly large. That's large. So you can safely assume that the sampling distribution of P is normal in shape, or very close to normal. There's a famous mathematical proof called the central limit theorem. The central limit theorem proves that the sampling distribution must be normal, or very nearly normal, if N is fairly large. The central limit theorem is one of the most famous proofs in statistics, and you should remember its name and what it proves. This fact that the sampling distribution is normal if n is fairly large, will turn out to be very useful, as you'll learn during the next few weeks. But I'll explain more about that later. The last topic we're going to discuss today in our review is we're going to review how to estimate the standard deviation from a histogram. Now remember, the standard deviation of a sampling distribution is called the standard error. I'll be using the term standard deviation as we talk. But if we're talking about a sampling distribution, remember that the official name for the standard deviation of a sampling distribution is the standard of error. So I might be a little sloppy when I'm talking about it here, but remember, it's really the standard error. Now, in the last lecture, you learned how to estimate the standard deviation from a histogram of a normal or normalish distribution. First, we estimate two scores, the score at the mean and the score at the 97.5th percentile. Here, those scores are 0.55 and 0.58. The z-scores of these two scores are 0 and 2, and that's why we estimated these scores in the first place. Two scores are two standard deviations apart. That means the distance between them is equal to two standard deviations. In this case, the distance between the two is 0.03. So if we divide that by 2, we get 0.015. One deviation is 0.015. Okay, now I want you to try it out for yourselves. This histogram shows the distribution of student scores on a questionnaire called the Empathy Quotient Scale. And this graph comes from the article whose name is given at the bottom of the slide. Now, I'd like you to estimate the standard deviation of the student scores using the approach I've discussed in this lecture and the last lecture. When you know the answer, or think you know it, write it down. I'll give you about 2 minutes to estimate the standard deviation, and then I'll resume. I'm going to stop talking now for about 2 minutes to give you time to work. Okay, I'm back. I hope you had success in estimating the standard deviation for this histogram. Here's the correct answer. For this distribution, the mean is 35.493, and the standard deviation is 9.63982. Now, I doubt that you estimated it was exactly 9.63982, which is about 9.5. But if you estimated that the standard deviation is 9, that is terrific. And if your estimate was anywhere between 7 and 11, that's still pretty good and shows you have the right idea. Now, let me quickly show how we estimate that the standard deviation is about 9. First, we estimate the mean. I've estimated the mean as 34, but any number between 33 and 36 would also be a good estimate. So you can see up in the right-hand corner of the slide, the true value of the mean is about 35.6, so even my estimate was off. Second, we estimate the score at the 97.5th percentile. Now, I estimated 52, but if you estimated any number between 50 and 54, that would be a good estimate. Next, we calculate the distance between the two numbers. The distance between 34 and 52 is 18. 18 is 2 standard deviations because 34 and 52 are 2 standard deviations apart. Finally, I divide the distance by 2, and that gives me 1 standard deviation. 18 divided by 2 is 9, so that's my estimate. The standard deviation for this distribution is 9, but it's just an estimate. The standard deviation is actually around 9.6, so an estimate of 9 is fairly close. It's definitely good, but any estimate between 7 and 11 would also be reasonably close. So we're almost done with today's lecture, but before we finish, let's sum up the main points. First, today we clarified the difference between 3 different types of distributions: the sample distribution of P, the population distribution of P, and the sampling distribution of P. I told you that I pointed out, I didn't have to tell, I just showed you that the sample distribution of P and the population distribution of P look a lot alike. The sampling distribution looks much different from these other two. So the sampling distribution is the oddball, the one that looks different, but it can make up for being an oddball because it's normal. Second, we learned that the mean of the sampling distribution of P is called the expected value of P. And we learned a surprising fact. The expected value of P in the sampling distribution of P is always equal to pi, the mean of the population. Third, we learned that the standard deviation of the sampling distribution is called the standard error. And we learned how to calculate the standard error using sigma, the standard deviation of the population. Fourth, we learned about the central limit theorem. This theorem proves that the sampling distribution of P is very close to normal if n is fairly large, meaning n over 30. Fifth and finally, we practiced estimating the standard deviation of a normal distribution from a histogram. So that just about concludes today's lecture. Don't forget to take the quiz that covers Chapter 9, Sampling Surveys and Political Polls. See you next time.